Wow, we are deep into the Laplace world, this world of Star Wars, where black magic allows us to rapidly cut through ODEs, send them into the algebraic space, and make our problem much easier. Now, one more very important theorem related to Laplace transforms that I wanted to discuss. The convolution theorem. Incredibly important, especially for numerical solutions to nonlinear equations can also benefit from convolution theorem. We're not going to cover any of the nonlinear dynamics in this class, but convolution is a generally super amazing and very important theorem. A lot of stuff that we need to invert back from the Laplace domain into the real space looks something like this. It's a product of two functions in the Laplace domain, capital F as some function of S and capital G as some function of S. The convolution theorem tells us how we can take a product of Laplace functions and send them back into the real space domain. So let's write some things down as prerequisite to the convolution theorem. Let's suppose that the capital function f and capital function g each have their counterpart in the real space. So we have little f, little g, where if you take the Laplace transform, they go to the Laplace domain. Now, the convolution theorem says the following about their inverse. Laplace transform function f and g, their product. The inverse is given by this mysterious looking integral. We have the integral of 0 to t, so that's the time domain that we want, of the product of the little f function and little g function, so the real space functions f and g, but their arguments are a little bit weird. So g just has tau in it because you're integrating over tau, so that one's kind of okay. But the f is shifted by that factor of tau. So it's f evaluated at t minus tau and g tau integrate over tau from 0 to t. Kind of weird. Alternatively, you can write it in this way, where you don't shift in the f function, so you keep f as just f of argument tau, but now you shift the g function here by t minus tau. D tau integrated from 0 to t. A little bit weird, right? So let's graphically illustrate what are we doing? I mean, physically what we're doing is we're taking a function and we're taking the other function and we're sliding that function with respect to each other, relative to each other, getting their product, and getting the integral under the curve. Let's draw a quick picture of what we mean by this. All right, so here's a brief graphical illustration of what we mean by a convolution. Suppose we had the two functions, f and g, that looks like this. Now what we're doing with this integral is we're taking one function and we're sliding, for example, in this case, g of tau, we're sliding this function freely along this tau axis, and we're convoluting the function g as it slides into the function f. And we're taking the product of g as it slides across f, taking the product and getting the area under the curve. And we're doing this from time t equals 0 all the way to some time t. So we're saying how convoluted, how overlapping are the two functions as you slide the two functions to each other from 0 to time t. That's sort of the essence of what we're doing with convolution. You're convoluting two functions. You're like sliding one function over the other, and you're looking at their products. Now, this type of convolution is, like I said, very common in many problems in science and engineering. We're going to eventually talk about Fourier series in a little bit, but a very common technique in numerical methods for nonlinear PDEs and ODE solvers is called spectral methods or pseudo-spectral method. In that technique, we're approximating functions with sines and cosines, which you will learn soon with the Fourier series. That's what we're doing at the Fourier series. But it also has a convolution. Whenever you have a nonlinear term present in your equation of motion, it's a product of two functions. And by going back and forth between Fourier space and the real space, you can nicely take care of nonlinear terms by using a convolution between a product of two functions and going back and forth between Fourier domain and real domain. And you can do the exact same thing with the Laplace transform. You can go back and forth between Laplace space and real space by taking products of functions and convoluting them. If that didn't make any sense, no worries at all. Just wanted to seed that little thought in there for your future research endeavors. But for now, just understand that the Laplace transform has this very cool theorem called the convolution theorem, where if you take the product of two Laplace space variables, if you want to bring it back into the real-time domain, you just have to evaluate this integrals. Let's do a quick example of the convolution theorem. Suppose we wanted to take the inverse of this quantity right here, capital Y of S. Now you can use partial fractions if you want. That's totally okay to do. I'm presenting you an alternative method to invert it back into the real-time domain. Now you can identify this as a product of two functions. Just like that. So I've rewritten this expression. First, pop the 3 outside because that's just a bystander coefficient. We have now the product of capital F and capital G, which can be separated into 1 over S and 1 over S plus 2 squared. Now, according to this rule, step number 1 is figuring out what is the Laplace transform little f and little g corresponding to capital F and capital G. Well, that's pretty easy to do because each of these terms are very easy to invert using the table. This will just be an exponential. This is just t times an exponential. Let's write those inverses down. Okay, we have here. I misspoke earlier. I said that the first term is an exponential. Not really. It's actually 1 over s. The inverse is just the constant 1. So there is no exponential involved in this case. The second term, though, does involve an exponential, but it has a factor of t multiplied out in front. We actually did an example like this last time, right? We had, I think it was row number 8 on the Laplace table, t times e to the negative 2t. So now we have these two inverses, little f, little g, that corresponds to the capital F and capital G. So now, according to the convolution theorem, all we need to do to find the inverse of the entire product is to just evaluate this integral. Now, you have a choice on which one to use. I said or. You could use either one. They're identical to each other. So usually, you want to use the easier version. Now, we have little f and little g over here on the right. We need to plug in and evaluate the times at these points, t minus tau and tau. It's your choice. You can choose whichever one you want to use. But this function over here is a constant function of 1. So there is no shifting involved for the constant 1 because it's always 1 all the way across for all time. And therefore, whether we shift it by a factor of tau, t minus tau, it's always going to be 1. So if you look at these two expressions, the shift is going to be the kind of the annoying one because you're going to have to carry around a shifting. For example, if you imagine using the lower definition, we have to plug in t minus tau in here. So you're going to get t minus tau e to the negative 2 t minus tau, and you have to integrate that thing. Kind of annoying. We're going to get t minus tau factors here. We don't want to deal with that. So we're going to use the top form, because if you use the top form, plugging in t minus tau into 1 is just 1. So we don't have to do anything with that. And then over here, g of tau is easy. It just becomes tau e to the negative 2 tau. So we're going to use the easier one, which in this case is the top definition. So here I've just used the convolution for the top definition, pulled the 3 outside. It's just the product of those two functions. Now, very easy. This first term just becomes 1 because f evaluated at t minus tau is still 1. It's always 1 all the way. Times g of tau is just simply plugging in tau there. just like that. So we get 1 times tau e to the negative 2 tau as the integrand, integral of 0 to t. That's it. So all we need to do is integration by parts. You just gotta do it. You do it once, and you get your final solution. It looks like this. All right, you do integration by parts, you get this solution right here. If I wrote it into each of its components, you can see that actually this example is the same example that we did last time using partial fractions. You get the same result, as we would hope so. So hopefully now you trust the convolution theorem. So you have multiple different techniques now. You can either use the partial fractions to break this term up into terms that you can invert easily, or you can use convolution theorem and integrate, and you should get the same result. So just another toolkit that you can use to invert from the Laplace domain back to the real domain, because like I said, that's often the most difficult part with Laplace transforms. Okay, so now I think we've done enough preliminaries and a couple of example problems. So I wanted to cover 2 more things this time. One, about how Laplace transform is incredibly powerful for coupled or a system of ordinary differential equations. And next, we'll do a physics example of a pendulum. And you'll see how the Laplace transform can handle weird functions like the direct delta function very easily. And that is an equation where if you tried to use normal methods, non-Laplace transform methods, you wouldn't really know what to do with these weird functions like the direct delta. We'll cover that next. Let's suppose we wanted to solve a system of coupled differential equations shown here. This is ODE, both first order in x and y, which are functions that you want. They're both a function of a single independent variable, time, t. Now you can see that the differential equation for x depends on the function y, and there's a separate differential equation for the variable y, which depends on x. So these 2 ODEs are coupled to each other. You're given the initial conditions that at time t equals 0, both x and y are equal to 0. Now, if you were posed with this equation prior to knowing Laplace transforms, you would do it in a brute force fashion. You would solve for one of the variables that you want. Suppose you solve for y. The top equation would look like this. I just solved for y. And then you would plug it into your bottom equation. And then you'd get a second order differential equation. And you get your first order one here, and you combine them. We don't want to do that. This is exactly how my brain was feeling when I was substituting terms in there, thinking, oh my gosh, I have to solve a second order equation. I only have first order equations and I have to frickin' solve a second order equation? Making me nauseous. No way. This is not what we're gonna do. You can definitely do this if you want to, but Laplace transforms is perfect and very powerful for these types of systems or coupled ODEs. Now you just carry through with the procedure. You take both equations, just take the Laplace transform term by term. Just like that, let's write down the equations and what you get. You get something that looks like this. The top equation is just the Laplace transform of the top evolution equation for x. So you just get this left-hand side, which is the Laplace transform of the first derivative. The right-hand side, just using the definition. Same thing on the bottom equation. This is just the Laplace transform of the evolution equation for y. Now, we can use our initial condition. Both of these terms are equal to 0 because we're given the initial condition that at time t equals 0, x and y are both equal to 0. Now, we're in a position where we have the variable capital X and the variable capital Y, both as a function of the Laplace variable s. And we have an algebraic equation, 2 equations with 2 unknowns. Now, I don't know about you, it feels a little bit cumbersome. You still have to solve a system of algebraic equations that are coupled to each other. 2 equations, 2 unknowns. You have to solve it. But it is easier than doing this, surely. right? This, you're doing the same thing. You're substituting one into the other, you're solving it. You have to do the same thing here. You have to solve for y, substitute in the other one, you have to solve it, but easier than this because you're solving an algebra problem instead. So 2 equations, 2 unknowns. Let's solve for capital X and capital Y. You'd get something that looks like this for capital X and capital Y. Again, we just had 2 equations and 2 unknowns. Algebra problem, you can do that. From here, you have a variety of different tools now to invert it back into the real-time domain. For example, you could use partial fractions. You would get something that looks like this. Partial fractions for the first capital X would just have these 3 terms. Partial fractions for capital Y would again just have these 3 terms. Okay, so you go to the Laplace table, you invert term by term. Actually not that hard. You might not even need the table at this point. We've done so many example problems at this point. So the first term looks like 1 over s squared. The very first example where we did the integration by parts and did the definition of Laplace transform was the Laplace transform of the function t. That was equal to 1 over s squared. So this inverse is just simply t in the real-time domain. So this will be t, this would be 2 times t. The second term, 1 over s, that was, again, one of our very early examples. 1 over s is just a constant back in real domain. It's 1, right? So this would be 1/3, also 1/3 over here. Finally, this one over here is just a time domain shift, right? So e to the negative 3t. Well, it's more of a shift in Laplace variable s. So in Laplace space, it's shifted by t s plus 3. Therefore, back in the real-time domain, you'll just get an e to the negative 3t. That's it. So we'll invert term by term. And there you have it. Our 2 solutions, little x of t, little y of t, which were the functions that you wanted to find. That's it. You just go through the Laplace transform technique by going through term by term, plugging your initial condition, using the definition, using an algebraic equation to solve coupled system of algebraic equations, partial fractions, invert term by term. Laplace transforms is incredibly powerful for these types of situations where you have coupled ODEs. Otherwise, you have to do this nonsense. Okay, so as I said, in science and engineering, coupled ODEs and coupled PDEs are so common that this is one very strong use of the Laplace transform. I'd like to do one final example in the Laplace transform chapter. But before we do that last problem, I wanted to introduce a very important function that we'll use in that last problem, but also generally useful for a lot of science and engineering problems. It's called the Dirac delta function. It's a very important function, and I wanted to teach you some properties about it. First, it's denoted by the Greek symbol delta. And here, the argument is at some time t minus a constant a. Something special happens at that value of a. Let's check it out. The function is equal to 0 for all time t when it's not equal to a, but it's equal to infinity when t is exactly at a. Kind of a hard function to think about. So it's 0, 0, 0, 0, 0, 0, 0, 0, 0, boom. At exactly position A, it spikes to infinity, and 0.0000 plus or minus immediately goes back down to 0. Okay, so let's draw a picture of what it looks like. All right, so let's draw a picture. It's 0 all the way across until the position A. So it's 0, 0, 0, 0, 0, 0, 0 all the way. All these points are 0. And exactly at t equal to a, it spikes, all the way shoots up to infinity. And then at a plus 0.000001, it immediately has to go back down to 0 again. So it needs to come back all the way down. And then it goes to 0 again for the rest of the time. Okay, so that's what the function looks like. 0, boom, pulses up to infinity, pulses back down, stays at 0. That's what the Dirac delta function is. What kind of function is that? Is probably what you are thinking. How would this ever be useful? Totally valid question. I will show you an example of that in the next one, the use of the Dirac delta function, but it's often also called a pulse function because a lot of signals in engineering are pulses. Think of an electrical pulse, especially like in electrical engineering, you have a signal that you pulse once, and you want to see what happens to that signal as a function of time and position. It's a very common concept in science and engineering. For example, if I have a beaker of water, I take some food dye, food coloring, get it in a little syringe, dip it into my beaker, inject it in the middle of the beaker. That would be like a pulse, a delta function of reactants or color at some position in time, position in the beaker, and also in time. So I would have a delta function in position and a delta function in time because I'm releasing the dye at time t equals 0 at that position, which is infinitesimally small. And I want to see what happens to that dye as a function of position and time. That will be your diffusion into an infinite medium problem. Again, a very canonical example problem that we use in science and engineering. So the Dirac delta function has a lot of uses, not just in time t, but also in position. So I've used time here because we've been using t a lot in Laplace transforms, but in general, it's defined across the entire number line. So it could be position x, y, z, it could be time. It's defined everywhere. The only thing you need to know is that at whatever position you specify at a, it jumps to infinity. Now, there's a related property about the Dirac delta function, which tells you about the area underneath this curve. So when you think about what is the area underneath this curve, it's kind of a weird question to think about. It's 0 all the way here, and at this point it shoots off to infinity, so you would think that a function shooting off to infinity would have infinite area underneath that curve at that point. But then this width is also infinitely small. So this is a function where at that point A, it shoots off to infinitely high, but the width of that pulse is infinitely narrow. So you're taking infinity and multiplying by something that's infinitely narrow, which is 0. And it just so happens that the mathematical definition and how we've defined the Dirac delta function is that the area underneath that pulse is exactly equal to 1. Just like that. So the integral of some variable t from negative infinity to infinity of the integrand, which is the Dirac delta function, this is literally the area under the curve, right? We're taking the area underneath this curve, and it has exactly 1. So now, in reality, the Dirac delta function is a really cool mathematical construct that has infinite tall, infinite narrowness. But in reality, a lot of times the Dirac delta function is approximated using a couple of different functions. For example, a Gaussian. A Gaussian is also peaked at some position, and it's got some width, usually the variance of that Gaussian distribution. And as that width becomes narrower and narrower and narrower, the peak gets taller and taller and taller. There are other mathematical functions that approximates the delta function, but that's the concept. In reality, it's a heavily peaked and pulsed function that gets taller and taller as the width gets narrower and narrower. And it's got the mathematical property that if you take the area under the curve, it's equal to 1. Now, a related integral property, which is very useful, is the following. So now what I've done here is to take the integral from earlier, but in the integrand, we're multiplying the Dirac delta function with another arbitrary function g of t. So remember the step function? That turned functions on perpetually and off perpetually. So it's very useful for situations like I'm going to add salt at a particular time point and just keep adding it, right? Boom, boom, and then it just keeps, it just continues in time. The Dirac delta function doesn't turn on and off a function perpetually. It's a pulse. So this integrand is saying, oh, I'm going to keep this function off at 0 the entire time, 0, 0, 0, 0, 0. So because you're multiplying with 0, right? This g of t function is 0 all the way outside of a. But then right when it gets to the point a, it is not only turning it on, it is making it jet off to infinity. Okay? Again, but with infinitely narrow thickness. So in this particular case, what happens is that you take the integrand, g of t, and you swap it with exactly the position where the jump occurs. So this integral is just equal to the following. So you just take the function g of t that's multiplied to the Dirac delta, you swap it at exactly t equal to a. So you evaluate the function g at t of a, because that's when the Dirac delta function pulsed that function exactly at that point. This is called the sifting property. This integral right here is called the sifting property and is also commonly used in math and sciences. Okay, now with our knowledge of the Dirac delta function, let's do our final example problem, a physics problem using Laplace transforms. Okay, let's do a cool physics problem. Actually, a pretty primitive physics problem using Laplace transforms. The cool part is the use of the Laplace transform, the Dirac delta function, to get a very nice physical answer at the very end. So, primitive physics example of a mass, a ball of some mass m, that is connected to a spring, and the spring is Hookean, in the sense that when it compresses or stretches, it has some equilibrium resting position that it wants to be around. And so it will generate a force that opposes it that linearly is proportional to the compressed distance x. Just like that. So whenever the mass spring moves by some position x, it's gonna have a spring restoration constant k, and the overall force on the mass will be equal to negative kx. Just Hooke's law, just a spring, a Hookean spring. Now we're going to track the position of this mass m. Just like that. So the mass m is at some position 0 at resting, and it's going to move as a function of x, and as it moves, it's going to experience a restoration force given by the Hookean spring, k times x, negative sign. Now, why would it move? It's moving because at time t equals 0, I'm going to take a massive hammer and whack the mass m. Just like that. I'm going to take a hammer at time t equals 0, whack, hit the mass. The mass is going to compress the spring. It's going to feel a restoration force. Now, at time t equals 0, I'm going to subject this mass to a force. And with the way we're describing it as a pulse, as an instantaneous hammer hit one time at time t equals 0, and then I don't hit it anymore. So it's a pulse. It's a pulse function. And we're going to approximate that force using the Dirac delta function that we just literally learned. In this case, the offset a is equal to 0. So at time t equals 0, we're hitting it. And therefore, it's just delta of t minus 0. Simply delta of t. Now, let's write down the equations of motion of this mass, because our ultimate goal is to figure out how this mass m moves as a function of time. So obtaining the equation of motion for position x as a function of time is our goal. We should obtain an ODE. So going back to your physics class, your mechanics, your introductory mechanics physics class, let's write down a force equation for the mass m. It will look like this. A force balance. Sum of all forces on the mass m. The acceleration looks like this. Mass times the second derivative of position with respect to time is equal to the external force that we supplied, F of t, that's the hammer, boom, and then the restoration spring elastic force, which is equal to negative k times x. So this term is simply going to be delta of t. Now, we have an evolution equation for the position of the mass x as some function of time. You could try to solve this, right? It's a second order linear ODE. But it's got this weird non-homogeneous term, right? Because you can bring this spring force over to the other side, so you get all the x's on the left-hand side, but this Dirac delta function is a non-homogeneous term. Now remember that tree diagram for a long time ago where I said the non-homogeneous term, if it's simple, you can use these techniques, method of undetermined coefficients, you could use variation of parameters. If it's weird, you can still use variation of parameters, but the Laplace transform can take weird functions pretty easily. Let's see it right here. We're going to take the Laplace transform of this equation and see what happens. So all I'm doing is, as usual, taking the Laplace transform of the whole equation term by term. Just like this, term by term Laplace transform. Again, looking at the first term on the left, the second order derivative with respect to time has these three terms. Again, go to that lookup table that hopefully took a snapshot of when I wrote down both equations. They were on this part of the board. The first derivative, the second derivative of a function. It looks just like this. The spring force moved over to the left-hand side is simply the definition of the Laplace transform capital X. And then lastly, we have on the right-hand side, the Laplace transform of the Dirac delta function, whatever that is. First, we could use the initial condition. So in this problem, initially, the mass is stationary. It's got zero velocity, and it's at the resting position, x equal to 0. Therefore, both of these go away because the initial condition, position 0, velocity is 0. Okay, so I just use the initial condition, 0 velocity, 0 position of the mass at time t equals 0. Now, let's handle this right-hand side, this non-homogeneous term. Laplace transform of the Dirac delta function. The function that's 0 all the way, and then it pulses out to infinity with 0 width, and then back to 0 all the way for the rest of time. Let's use the definition of the Laplace transform. Here's the definition of the Laplace transform of the Dirac delta function. So just take the function that you want to take the Laplace transform of, slap it on with e to the negative st, integrate dt from 0 to infinity. Now, we could use a shifting function because this e to the negative st is like our g of t. Now, earlier I defined it from negative infinity to infinity. It's okay in this case because the Laplace transform goes from 0 to infinity, the pulse is happening at 0, so we're okay. So we can just simply replace this function e to negative st, evaluate it at t equal to 0. Just like this, e to the negative st, that's the integrand earlier where I had g of t. Evaluate that at, in this case, a is 0, so t is equal to a, which is equal to 0. We evaluate t equal to 0, this is simply equal to 1. And actually, if you go to the Laplace table shown right here, you can see that the Laplace table for entry number 13, row 13 down here, has a Dirac delta function, Dirac of t, which is simply equal to 1. Okay, so we just showed using the definition that the Laplace transform of the Dirac delta function is simply equal to 1. It exists on the Laplace table. Okay, so now I'm going to erase this side calculation because we now know what this is. This is just simply equal to 1. Okay, so now we have simply an algebraic equation for capital function x. Let's solve for x. Okay, all I've done here is to simply solve for the function we want, which is capital X. So we have ms squared, k on the denominator, the 1 that appears in the numerator on the line below. I've simply pulled out the mass m, factored it out so that it looks like s squared plus k over m. Now I'm going to take this equation, rewrite it in a slightly different way, and I'll explain why in a little bit. Okay. All I've done here is a small little algebra thing where I've multiplied by this factor of square root of m over k, the mass of the ball divided by the strength of the Hookean spring, and multiplied by the inverse of that exact same ratio, k divided by m square root. So this prefactor times this other factor multiplied together will just simply equal to 1. So I just multiplied it by 1. Why did I do this? Because we're at the final stage of the Laplace transform approach where we have to now invert this solution back into the real domain, right? We had our ODE, we didn't want to solve it because it had this weird delta function thing. We took the Laplace transform term by term. We got an algebraic equation. We took care of the Laplace transform of the Dirac delta function by using the definition. And we now have our solution to the algebra problem, which is the solution for capital X as some function of S. Now, final step, invert it back into the real-time domain. And we need to use the table. So let's go to the Laplace table. Keep this function in mind. So this is something that looks like a constant. We have some factor divided by s squared plus that factor squared. All right, let's go to the screen and let's go down our Laplace table to see if anything on the right-hand column looks something like what we have here. Factor square root divided by s squared plus factor squared. That's what we're looking for. Okay, so none of these look relevant because we're looking for like a 1 over s squared plus something. So none of these look good. Not quite, because that term is going to have a cross term. That's going to have s squared minus 2as, and our solution here doesn't have a linear and s term, so it's close but not quite. These guys also have a cross term on the bottom. They also have cross terms and no exponential. So let's go to the second page over here. Log terms doesn't look right. Okay, so this looks more promising, right? So everything here on the right-hand side looks more promising. Do any of these look good to you guys? Row number 17 looks really good because row number 17 has some constant omega on top divided by s squared plus omega squared. See that? And if we come back to the board, you can see it is that. We have some omega up here. So this whole thing might be omega divided by s squared plus omega squared. Right? So we could just directly use row number 17. And actually, let's go back to the screen here. We can see row number 17 has omega squared over s squared plus omega squared. And its inverse is sine omega t. So that omega factor must be the frequency of the oscillation. And the fact that we get a sine is pretty encouraging, because you would expect this problem to have a sine hidden in there somewhere. Back and forth, back and forth, back and forth. Okay, let's write down row number 17 here and see how we can map this equation to row number 17 and get the inverse. So here's row number 17 on the Laplace table. And you can clearly see that if this factor down here is equal to our frequency omega, then that factor just becomes omega squared. And we have an exact mapping of the right-hand side of row number 17 with this term that we need to invert back into the real-time domain. So from this stage, we could just write down the answer for the real-time domain, which will simply look like sine omega t. All right, we have our final solution. The position of the mass x as some function of t is the inverse of this algebraic solution that we got, capital X as some function of s. So I've just literally taken this term right here, plugged it into the inverse. Using row number 17, we massaged the original solution such that we were able to identify omega, a frequency, which is equal to the square root of the stiffness of the spring K divided by the mass of the ball m. And it's simply equal to 1 over m times the omega, the frequency, times sine, the argument of frequency, times time. Now, this is a very important point. Whenever you end a mathematical problem like this, think physically about whether your solution actually makes sense. First physical check. Does it really make sense that you have a sine as a part of your solution? You see that the pendulum goes back and forth, or a spring goes back and forth. They map onto the same problem. So a pendulum go back and forth, back and forth. That looks like a sine function. So good. Physical sanity check. It looks like a sine function. That's consistent with our life experience of pendulums and spring-loaded masses. The frequency, omega, says that if we have a very, very stiff spring, right, very elastic, stiff spring, then the frequency should be very high, meaning that the mass will go very, very quickly, just vibrate back and forth extremely quickly at large frequency. So I have a stiff spring, I take a hammer, whack it, it's gonna vibrate very, very quickly. Yeah, that kind of makes sense. That makes sense. If I have a stiff spring, I whack it, it's gonna have a very high frequency. Kind of makes sense. So the sanity check of the frequency of omega going up with the stiffness of the spring going up also makes sense. Same with the mass. If you make the mass very, very, very large, so that the ball is a massive object, you whack it, you'd kind of expect it to go slowly, right? Because it's such a massive object that's just gonna vibrate or go back and forth extremely slowly. Therefore, the frequency goes down. Again, sanity checks based on what you physically would expect from a system like this. Now, there is one last thing that doesn't really make a lot of physical sense. So when you think about a real pendulum that you whack, that goes back and forth, back and forth, back and forth, there is one key gap that doesn't seem consistent with our life experiences. Usually when you take a pendulum that goes back and forth, eventually it'll come to rest. It dampens out and comes to rest. But this solution says that the sine omega t, that amplitude goes from 1 to -1, 1, -1 for infinite amount of time. And it's got the prefactor that's also constant as a function of time, 1 over mass times frequency. These are all constant values. So it's telling us that the position of the mass will forever not dampen. So the pendulum will forever just keep going and going and going perpetually until the end of time. What are we missing? What piece of physics are we missing? Of course, we're missing friction. We're missing friction or viscosity of the surrounding medium or the friction on the surrounding environment. So in reality, we would have an additional term in the equation of motion that accounts for friction. So I've added one way to represent that friction as simply some constant eta, which is the damping factor or the viscosity or the frictional coefficient, times the velocity of the spring, which also kind of makes sense because when a mass is moving, that friction should be proportional to how quickly it's moving. Now, when we cover the entire subject of fluid mechanics, you'll learn that the way in which it depends on the velocity could be linear, it could be quadratic, it could be other dependencies, but the easiest possible case is linearly proportional to the drag. And in the field of fluid mechanics, it's called Stokes drag or creeping flow, where the motion is so steady and slow that the frictional coefficient is simply viscosity eta times the velocity linear scaling as the speed. So now, if you were to repeat this calculation all the way through until the very end, you should find, going back to the Laplace table over here on the monitor, you can see that there are terms in the left-hand side that has an e to the at times sine omega t. So if a in this term were equal to the damping, were a negative number, then you have e to the negative t times a sine, so it would dampen as a function of time. So in our ideal case, in the absence of friction, the solution will just go up and down, up and down. The amplitude will never change, all the way out to infinity. But with friction, we'll have an exponential damping term, and therefore it will decay as a function of time, just like that. And at time t equal to infinity, it will decay, and it is now consistent with what you would expect physically with the pendulum should eventually dampen and come to rest. All right, that's it for Laplace transforms. I just wanted to finish with this one really cool physics, primitive example of physics, but a cool application of the Laplace transforms. All right, next we're going to start a brand new chapter. So we're all done with Laplace transforms. See you next time.